I run the Aeromechanics and Evolutionary Morphology Lab at Brown University, where we use bats as our primary subjects. We study how bats are able to fly and use this information to do all kinds of work. We take a unique approach to studying animal flight that deeply integrates the biological and physical sciences. And by integrating these two approaches, we're able to learn things that we can't learn by taking any single approach by itself.
So in addition to putting live animals in our wind tunnel and making measurements of their kinematics and their motion and also the flow fields associated with them, we can also put in engineering models that are inspired by the bats. So for example, robotic bat wings, this one can flap, it can move forward and backwards like that, it can fold, and it's all controlled by these tendons which are driven by servo motors underneath the model.
I was very excited when I heard about the Hyundai Visionary Challenge, because I believe that engineering solutions to understand animal flight are very important. And bats are incredible at flying, of course, but working with live animals often adds like a very different layer of complexity. Think like behavior and training and other things that you cannot really account for.
I don't think that the end result is to replicate a bat entirely. I think that smart mobility is about creating by finding inspiration everywhere you look. We just chose to look at bats mainly because of their ridiculous aerial skills. They're really fun creatures to work with and fascinating to watch. I'm particularly surprised about how they dominate their inertial moment using their wings. They regain control of perturbed flight with minute modulations of just a single wing beat.
So from the live animal measurements, what we want to learn is how is it that the bats are able to fly in these adverse environmental conditions, how they can manage to fly with agility and with maneuverability in unsteady environmental conditions. Then we want to take that understanding and use that to build inspired models, engineered models that can be applied to personal air vehicles, to drones, to small flying vehicles that will also be able to survive and also be able to thrive and manage robust flight in unsteady environmental situations.
This approach lets us pick out the traits of a flying animal that are most valuable for human engineering. We could make something that is a better flyer than any living animal, because an animal has to carry out all kinds of activities that no machine would ever have to do. A machine doesn't have to mate or raise young, but we can identify the things about a flying animal that we can abstract and put into an amazing human engineered device.
So our proposal is to improve our current engineering and robotic solutions so that we can tune out the interesting things that we have observed in our live bats, isolate them, and study them in detail. The better our engineered system is, the more I can say that we understand how bats fly. And in addition, of course, the better our engineered system is, the more I can say that we're slowly constructing a baseline for the future of flying devices.